Hello everyone, this is Eckel from Fraunhofer SIT in Germany. Today I'm here to present you our paper on Userspace software integrity measurement. We are in the SEC Health workshop. That is why we now first look at the challenges in Healthcare 4.0. Healthcare 4.0 consists of services and infrastructures which are highly interconnected, heterogeneous systems consisting of sophisticated cyber-physical systems and IoT devices. These usually operate unattended and are always on. That makes them vulnerable to a variety of cyber attacks and advanced persistent threats. And developing appropriate countermeasures is complex and difficult, and research has shown to be interdisciplinary in this area, which involves network security, cyber resiliency, anomaly detection, and integrity protection. In this paper, we focus on integrity protection. Since we make heavy use of trusted computing, let's first define what trusted computing is. With trusted computing, the computer will consistently behave in expected ways, and those behaviors will be enforced by computer hardware and software. Enforcement here is quite a strong term. Trusted computing today is also, or rather used for detection instead of enforcement. That's why I have a small addition to this. As an alternative to enforcement, misbehavior can be made detectable at a later time. In our paper, we make heavy use of the Trusted Platform Module TPM. So let's first define that. A Trusted Platform Module is a cryptographic coprocessor in hardware with secure storage and secure key generation capabilities, and it is hardened against physical attack. A TPM is always passive, and software has to use it, such as the UEFI, the bootloader, OS kernel, or apps. TPM is also known as a crypto decelerator because it's just slow. Let's now have a look at the problem that we try to solve with our paper. As you can see here, we have depicted a boot process, and the problem lies with the measured boot process. When the system is powered on, the first component that is executed is typically the BIOS or UEFI. It executes its main logic and then, in a classical boot process, passes control to the bootloader. But in a measured boot process, before passing control, the BIOS or UEFI measure the bootloader, store or irrevocably anchor this measurement into the TPM, and store an entry in the boot log. This process continues. The bootloader measures the OS kernel and then starts it, and then the OS kernel is in control. Part of the OS kernel, the Linux kernel, is the Linux Integrity Measurement Architecture, IMA, which is responsible to measure apps. In this case, the OS kernel stays in control, and of course it doesn't pass control to apps. Entries are stored in the IMA log. So all OS software that is executed is stored in the IMA log and also anchored into the TPM. Apps themselves can also be interpreters, which means they execute code somehow. These can be scripts. An example is the Java virtual machine, which can also load Java classes executable code directly from the network into the main memory for execution. And IMA doesn't see that. It operates on a file basis. Java classes can also be part of the critical system state, critical system security state, and must be measured. And that's the problem here. At the moment, scripts are not measured, and that's what we try to solve in our paper. Consequences. It is important to verify a system and all of its components in depth, according to the principles of system transparency. This starts with hardware and scattered firmware in every single hardware component that should be measured, and scattered software, which also consists of libraries, configuration files, and so on. Interpreters or software may load executable scripts over network, like Java virtual machine. And this goes undetected by Linux IMA. Attacker may inject malicious code this way. We just saw how software can be measured. How can we make use of these measurements? The process is called remote attestation, which basically means to verify the integrity of a target device from remote. In the graphic here, you can see an attester on the left, the target device, and on the right, a verifier who wants to verify whether or not the attester is in a trusted state, which means it wants to know whether or not it executes only authentic software, known good software. So for that purpose, it requests the operational state and receives in return the boot log, the IMA log, and TPM signed evidence of this boot state, because the logs are anchored in the TPM. And when the verifier verifies the digital signature of the TPM and checks the log integrity against the TPM stored values, and then compares the hashes of the software to known good reference values. And if everything matches, then the attester system, the target system, can be considered trusted and integral. Our threat model is the following. An adversary aims to execute arbitrary code undetected on the attester system, and the adversary capabilities are: has physical access to the attester system, is able to eavesdrop on communication channels, and record, modify, and replay messages between attester and verifier, and it is able to modify, replace, and execute boot and OS software, including the UEFI bootloader, OS kernel, and so on. Adversary non-capabilities, it is not able to hijack running software processes in memory, for example, by exploiting software vulnerabilities, buffer overflows, and so on. And it is not able to compromise the TPM physically or by software, because the TPM is considered in our security model as hardened against such kind of attacks. Our first contribution in this paper is to introduce Userspace software integrity measurement. For this purpose, we introduce a library and a service. The library is part of an app interpreter and reports measurements of scripts and Java classes in case of the JVM to a central system service, the Usem service, which manages connections and measurements from multiple applications. And measurements are stored in the PCR log and anchored in the TPM. PCR stands for Platform Configuration Register, not to be confused with PCR-based testing for the coronavirus. And this PCR log is then also reported in a remote attestation process to a remote verifier. Our second contribution is highly frequent logging. So instead of measuring files or executables one by one into the TPM, waiting for the slow TPM to finish the anchoring, we instead consolidate multiple measurements into one, which means we hash them together and extend this hash to the TPM or anchor it in the TPM. And this speeds up the whole measurement process. So in the graphic here, you can see a Usem client, such as the JVM, which connects to the Usem service interface. And then the requests are handled by the client handling. There's an in queue and an out queue. In queue is called measurement queuing. And the heart of our highly frequent logging facility is the PCR measurement handler. PCR, again, is the platform configuration register in the TPM. And as long as the TPM is busy, incoming requests for measurement are stored in the waiting queue. And as soon as the TPM is ready, this wheel, this tri-state queue here turns, the waiting measurements become processing. They are hashed together by the measurement aggregator. And then these are extended into the TPM. As soon as this process finishes, the wheel turns again and the measurements become ready. They are forwarded to the measured entries queuing, which goes back to the client handling. And the client handling is responsible to send the measurement confirmations that measurement was successful to the Usem clients. We implemented our contributions as a proof of concept, and the hardware that we use is a Raspberry Pi Model B with Raspberry Pi OS Lite Buster from January 11, 2021. It is equipped with a TPM, or Let's Trust TPM, which basically is an Infineon TPM 2.0. All source code is written in Portable C99, and the source code is available on GitHub via the links that you can see here. There's the Usem library, the Usem service, and our adaptations to the Java virtual machine. Again, this code is proof of concept, no warranties or guarantees from our side. As part of our proof of concept implementation, we modified the OpenJDK 11 Java virtual machine. For this purpose, we added a Usem library call to add entry, which is part of the Usem library, in the function class loader load class of the OpenJDK file source hotspot share class file class loader.cpp. And as you can see, in line 1483, we add a call to our Usem library function add entry. The first argument is the PCR number of the TPM, in this case 23. The second argument is the producer name, in this case Java load class. Then we have a class name, which is part of the log entry. Then we have the binary buffer of the Java class and the length of that. The add entry function hashes that and calls the Usem service to extend it to the TPM. In order to underline the feasibility of our contribution, we back it with performance measurements. As you can see here in red, that is anchoring a single entry one by one into the TPM compared to multiple measurements combined. In this case, we combine 20 measurements into one and then anchor it in the TPM. And as you can see here, for 2000 measurements, it's much faster. Actually, it's 18 times faster. For 2000 measurements, in a multi-record scenario, it takes 2.5 seconds, while in a single record scenario, it takes 45 seconds. In a second step, we compare different numbers of measurements combined into a multi-record, and the results are the more entries per multi-record, the more efficient the measurement process becomes. As you can see on the left, the dashed line with the red dot is n equals 100, and it's the fastest. Adding to that, we have a table with actual measurement values. On the last row, you can see our example with 2000 entries to measure. For single records, you see it's 45 seconds. For n equals 20, it's 2.5 seconds. And for n equals 100, it's 0.6 seconds. In the first row, you can see that we have 10 entries to measure. And for a single record, it takes 0.236 seconds, while for n equals 20, it's 0.061 seconds. An interesting thing is that for n equals 100, it's almost the same as for n equals 20, 0.064 seconds. At the end, we identified some potential future work topics. First, shell scripts are also essential for Linux-based operating systems, such as bash scripts. They should be measured too. Using our Usem library, for example, the bash interpreter could be augmented exactly as we did with the JVM. Second, interactive commands. With our contribution, also interactive shell or repeat, evaluate, print loops, commands can be measured. On the verifier side, sure, this requires more effort to make sense of these commands because these are interactive user commands. Perhaps the solution is to use artificial intelligence techniques to determine if a command is suspicious. Third, our highly frequent logging facility could be implemented into Linux IMA, so into the Linux IMA kernel implementation to speed up the measurement process. Conclusion. The problem. It is essential to verify the integrity of a system and all of its components in depth. But currently, neither measured boot nor Linux IMA measure scripts, at least not those that are loaded from remote locations directly into the memory for execution. Our contribution is we enabled interpreters to measure scripts and others and anchor them in the TPM and a separate log, the PCR log. We optimized the measurement process with highly frequent logging on the slow TPM. We provided a proof of concept implementation, the Usem library and the Usem service. Then we augmented the OpenJDK 11 JVM with our Usem library to measure Java classes. Also provided performance measurement to underline the feasibility of our contribution. Thank you for listening, and now I am happy to answer any questions you may have.